Welcome back to the deep dive. Today, we're getting away from all the hype around AI models and looking at where the rubber quite literally meets the road.
Or in this case, where the box meets the belt.
Exactly. We're doing a deep dive into how reinforcement learning RL is creating these truly self-optimizing conveyor build systems.
And specifically during facility build-outs, which is a really chaotic environment.
It is. And, you know, if you think conveyor belts are just these dumb tracks moving boxes, you're missing a huge piece of the puzzle.
Oh, absolutely. They're the lifeblood, the whole circulatory system for manufacturing, warehouses, you name it.
And optimizing them gives you this incredible return. We're talking huge cuts in energy use, less downtime, and just a massive leap in productivity.
Right.
So our mission today is to really get into how RL delivers that kind of intelligence right from day one of a new facility.
And that new facility context is just so important. The big problem has always been dealing with change.
Because things aren't static.
Never. Traditional systems are built on these fixed models of how much stuff they think they'll be moving. But in a build-out, you're adding new lines, changing routes. Those old rules just break. RL is what lets the system learn and adapt on the fly. It's always trying to find the best way to work, even when its whole world is changing around it.
Okay, let's unpack that. I mean, we all hear about AI all the time. What makes reinforcement learning so different from, the other types of machine learning people might be familiar with?
It's a great question. The biggest difference is that RL doesn't need a giant pre-labeled data set to get started. It learns from experience.
Okay.
I mean, think of it like you're training a puppy, but a digital one. The agent, that's the AI, interacts with its environment, which is the conveyor system.
Right.
And it gets feedback. A reward for doing something good, like moving a box efficiently, or a penalty for something bad, like causing a jam or wasting power.
So its only goal is to get the most treats, basically.
Exactly. It wants to maximize its total score, its cumulative reward over time. It's not told the right answer. It has to figure it out by trial and error.
Which is so different from supervised learning, where you'd have to feed it millions of examples of this is the perfect speed.
Precisely. With RL, it runs millions of its own experiments, either in a simulation or in the real world, to discover what works. For a facility that's changing week to week, that is just invaluable.
No reprogramming needed.
The system reprograms itself.
So let's ground this in the physical world for a second. In this conveyor system, what's the agent and what's the reward?
Good question. The agent in this case is usually the central controller, the logic unit that's running the whole show.
Okay.
The state is a real-time snapshot of everything. Current belt speed, how many items are on the line, the energy draw, all of it.
And the action is what it decides to do.
Yep. Speed up, slow down, reroute a package, and the reward function. That's where the magic is. It's a formula that you, the operator, define. So you'll design it to give a big reward for moving lots of items per hour, but also a big penalty for things like creating a bottleneck or using too much energy. That negative part is key to making it efficient, not just fast.
That makes so much sense. It's like it has its own internal budget. Now let's get into the nuts and bolts. The sources point to 4 main pillars of optimization here. Let's start with speed regulation.
Speed seems so basic, but it's critical. If you just run everything at max speed all the time, you're burning energy and creating traffic jams downstream.
But if you go too slow, you miss your targets.
Right. So the RL solution is constantly looking at the queue depth, how many items are waiting down the line, and the volume of stuff coming in. It learns to predict peaks.
So it's not just reacting, it's anticipating.
Totally. It might learn that, every day between 2 and 3 p.m., the sorting area gets hit with a 10% surge. So it'll proactively speed up the main belt at, say, 1.45 p.m. to clear the way. It manages the flow before a problem can even start.
That's incredibly smart. And that kind of predictive control leads right into the second pillar, load balancing.
Yeah, because you're not moving identical boxes. You've got big things, small things, heavy, light.
And if you just throw them on randomly, you're going to wear out certain parts of the belt and motors way faster?
For sure. The RL algorithms here act kind of like a super efficient Tetris player. The sensors see the size and weight of an item coming in.
And the system figures out the best place to put it.
Exactly. It calculates the ideal spacing and position to spread the load evenly across the entire surface. This massively reduces wear and tear.
But what happens when something new shows up? Like a new product with packaging it's never seen before. Does it just break?
That's the beautiful part. It doesn't need to have seen it before.
Oh, interesting.
Because the reward function isn't about identifying the item, it's about minimizing strain. It understands the physics. So it sees this weird new shape. It might try a couple of placements, and within seconds, it learns which one leads to the best reward, the lowest strain, the smoothest movement.
It generalizes.
It adapts, and that adaptability is crucial for the third pillar, routing and switching.
Right, because in these massive distribution centers, you've got dozens of junctions and possible paths.
And the old way was just a simple, if this, then go that way logic, very rigid.
Very easy to break.
RL takes a totally different approach. It's always weighing the cost of every possible path. It asks, what's the current traffic on Route A versus Route B?
And it can see if a belt is down for maintenance or something.
Exactly, or if there's a small jam starting to form 50 feet ahead. It takes all that real-time data into account and can instantly reroute items on the fly to avoid a problem. That prevents those cascading delays that can shut down an entire line.
And that brings us to the fourth pillar, the one that probably gets the CFOs most excited.
Yes. Energy optimization.
For any 247 industrial operation,
Yeah.
the power bill from thousands of motors has to be just astronomical.
It's a huge operational cost, and the RL system tackles it directly.
Yes, so.
Instead of just running a motor at 100% power all the time, the agent learns the precise amount of power needed for a given task. If it's moving one light box slowly, it might only need, say, 42% power output.
So it's modulating the power in real time based on the actual load.
Minute by minute. And when you add up those savings across thousands of motors over a year, it is a substantial amount of money and a big win for sustainability.
So if we pull back and look at the big picture here, the real benefit isn't just a faster belt. It's a whole new kind of industrial infrastructure.
It's self-governing infrastructure, it's more resilient, it's smarter, and it's built to scale.
Okay, let's quickly recap those top-line benefits for you. First, you get improved efficiency. The system is always learning, always getting a little bit better.
Then there are the cost savings, which come from everywhere. Lower maintenance from better load balancing, less downtime from smart routing, and of course that big energy saving.
Third, and this is so key for a new facility, is scalability. You can add a whole new wing to your warehouse, and the RL agent just sees it as a new part of its environment to learn. No massive reprogramming project.
And finally, there's just raw flexibility and adaptability. Traditional systems break when something unexpected happens. RL systems thrive in chaos, a sudden surge in orders, a change in materials. It just recalculates and finds the new best way forward.
And this isn't science fiction. This is happening now. The sources cited some big names already using this.
Oh, yeah. The prime example is Amazon. They use RL all over their fulfillment centers. Their big challenge is that wild swing in demand, right? Black Friday versus a normal Tuesday.
The huge difference.
By using RL, their conveyor systems can adjust speeds and routing based on the real-time order queue. They run smarter, not just faster, when it really counts. And they've shown it directly reduces the cycle time, how long it takes an item to get from a shelf to a truck.
And what about outside of e-commerce?
The auto industry is another big one. An assembly line is all about precise timing. They're using RL to predict tiny slowdowns in the parts delivery conveyors and adjust the upstream flow to prevent a bottleneck. Even shaving a few seconds of wait time for a key component on the main assembly line can translate into millions of dollars.
So to wrap it all up, reinforcement learning isn't just some small upgrade. It feels like a truly transformative solution here. It creates systems that are always optimizing themselves, balancing speed, load, routing, and energy.
The end result is just smarter, more efficient, and ultimately more cost-effective operations all over the world.
It really is.
And this all raises a really interesting question for you, the listener, to think about. Considering how fast all this is developing, what's next? I mean, sensors are getting better, AI algorithms are getting more efficient, the hardware is getting cheaper. Future systems will be able to pull in data from way outside the facility walls, maybe from the entire supply chain. So how will that ability to manage ever more complex dynamic environments redefine how we not only run our facilities, but how we actually design and build them from the very first blueprint?
A fascinating thought. The future of industry is definitely autonomous. Thank you for joining us for this deep dive into the intelligent, moving parts of our world. Keep exploring that intersection of AI and efficiency.